Thanks for joining us today. Today we're going to be talking about lesson 9-1, trigonometry with the calculator, and the graphs of the basic trig functions. This lesson is more or less the last bits of pre-calculus trig functions that we need to clean this up. If this is unfamiliar for you, if this is hard for you, we can do a lot more practice. We can get a lot more help. But if it is familiar, that's good. This should be all the review you need, plus doing the homework, obviously. Before we go on, it's important to note this is the last unit. Unit 9 is the last unit of AB. So if you're watching this video, congratulations for making it this far. Only a few more lessons and you'll be done with the AB curriculum. Congratulations. So when you're using a calculator for the trig functions, it's important to set the calculator into the correct mode, radians or degrees. In calculus, we'll almost only use radian measurement. So when we're talking about correct mode, you want to be sure you're in radian mode. To review how to go into that, we're going to take our calculator out, mode, and the third or fourth option down should be radians versus degrees. Radians should be in black, it should be highlighted in black, it shouldn't be flashing unless you're highlighting it like this. Second, quit, back to the home screen. And now we're just good to go. You should have no problem doing these three. Go ahead and try it out. Unpause the video when you get the right answers. 3, 2, 1. So the first thing we should try is sine of 2. 0.909. If you didn't get that, your calculator is probably not in the right mode. I don't know how else to tell you. 909. There's very little you could type wrong there. Careful, careful. I'd be impressed to hear about people who did get it wrong. Tan, negative, where's pi? It's right above the caret. Second pi, second caret, divided by 5. Enter. And we get negative 0.726 if you truncate. Or, if you're the normal person, 0.727. Rounder. Secant 1.3. Now this is the only hard one, quote unquote. Secant is not one of the buttons on your calculator. Nowhere to be found. It is not cosine inverse. I want you to know that. I need you to know that. You need to write it as one of the basic functions. It is not. It's very confusing, but it's not cosine inverse. Secant is not cosine inverse. Secant is 1 over cosine. And your use of exponents was what's going to screw you up here. These are not the same thing. These are not the same thing. No, 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 no. All right. So we just have to type this in the calculator and we're good to go. So 1 divided by cosine 1.3. 1.3, not 1 point negative. 3.738. Done. 3 point? I'm right under my mind. 3.738. Done. Okay. Let's try to use some more interesting applications. Nope. Let's use some more interesting applications in the next examples. Use a calculator to find the missing measure in each triangle. So, using what you know about trig so far, you should be able to set up an equation for both of these. A trigonometric equation, an equation with a trig function, and solve both of them. Try it out. Write something down. If you really get stuck, unpause the video, maybe pause it again. 3, 2, 1. Did you pause it? Did you try it? I don't know. So we have this little angle here. A lot of people like to ask me, what the heck's r? Why is it an exponent of r? What does that mean? I swear I told you. Exponent of r is like asking, Mr. Leven, I don't understand. What's this exponent of 0? What's this O? What's this O floating here? That's 360 degrees. This is 0.5 radians. You don't have to write that. It should be sine of 0.5 equals 5 over x. If you're saying there, how did I get that? How did he get that? I don't know. 0.5 is across, is opposite this side. That's what makes the side opposite. And x is across the hypotenuse, across the right angle, so it's the hypotenuse. And which trig function uses opposite and hypotenuse? Which of the basic trig functions uses opposite and hypotenuse? It's sine. Now, how do we solve this? I hope you didn't type in sine of 0.5. That's not right. What you want to do is multiply both sides by x. We want to keep sine of 0.5 as long as possible so we avoid any rounding errors. So we're going to manipulate it like this. X on the outside is x times sine. And now we're going to divide both sides to isolate x. And this is what we're going to type in the calculator. This is an exact value for x. An inexact value would be 5 divided by sine 0.5. If you're ever wondering how to tell if the problem's in radians or not, it's always in radians. It's in radians unless it tells you otherwise. And we get 10.429. So this is an inapproximate answer. This is an approximate answer. That's an exact answer. All right, if that was new for you, you should try this one out. It's not that bad. Go ahead, try it out. Do you have an equation? Do you have an answer? Figure out which sides first. So looking at my angle, this guy is across from it. This guy is the opposite side. And this is the hypotenuse. So that must mean he's the adjacent side. Which function uses opposite and adjacent? It would be tan. So tan of the angle, not tan of 2 over 5. Tan of this angle is 2 over 5. So how can I get theta by itself? Well, getting theta by itself is the same we've been doing for the whole course. We're going to use an inverse function. So what we have here is, let's say we had root theta. How would you get theta by itself? You would square both sides. What if we had theta cubed? We would take the cube root of both sides. These are inverse functions. If this was e to the theta, I would have log both sides. We want to get, we want to use the inverse function. So the inverse function for tan is tan inverse. Now this is really bad notation, as I mentioned, but this is what tan inverse is used for. This is what that button on your calculator is used for. A better notation that we'll use in this class would be theta equals arctan. Now people don't like that too much, but it's necessary. It's a much better notation, and it's necessary to know both. So that's the better notation, not that. Either way, you have to know both. Both will show up on the AP test. We're going to do second tan, gets us tan inverse of 2 over 5. And we get 0.381 if you're a rounder. Good person. Or 0.380 if you're a truncator. Hidden down there. So if you wanted to, you could try out some problems now from the review set. Some good review problems would be, of this sort, would be, I don't know, try examples, problem, I don't know, what do they call them on the other sides? Problems 1 through 7. You should be able to do 1 through 7 here. No big deal, no big problem. On the homework. So you can pause the video, come back to it after you finish those. Here we go, but I'm going to keep filming because this is not going to be a super short video. All right, graphs of trig functions. So trig functions are periodic. What does that mean? Their graphs repeat. They're repetitive. They repeat. After a certain period, or just a cycle, in other words, after a certain length of time, it just starts over again, like the Earth revolving around the sun. The sine, cosine, cosecant, and secant functions, blah, are all having a period of 2 pi. It takes them 2 pi long to repeat. Tangent and cotangent, on the other hand, are the weirdos, and they have a period of pi. So tan and cotan have a period of pi. All the other guys have a period of 2 pi. It's important to remember, you should be able to easily graph these by using these 4 values and by using the fact that the graph repeats. You should know these values into each of these functions basically by now. If you don't, get to memorizing. And then the other exception is we should know this one for tan and cotan. Why? Do you know? Can you tell me? It's because tan of pi over 4 is 1. So it's a nice output. It's a nice input-output relationship. All right, without further ado, here we go with the graphs. Now, if you can recall these graphs, this is not with a calculator. You need to be able to do this by hand. If you can recall the graphs, draw them. If not, I'm going to go nice and slow here. So I'm going to graph each of my x values as thetas, as angles. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi, 0. Sine of pi over 3 pi over 2, negative 1. Sine of 2 pi, 0. This works backwards the same way. This is what it means to be periodic. You should recognize sine pretty quickly. It's a nice wave. It should be nicer than that. I'm going to give it one more shot. Here we go. I don't know if you can hear the pen I have going. I can hear it though. Headphones. This is okay. I've graphed better sine functions. I've graphed worse sine functions. We're just going to do it one more time. Feeling self-conscious today. This is fine. Yep. You know what? All right. So here's the lesson. Like I always say, the calculators people won't care if you can draw it nicely. They'll care if it's accurate, relatively. You have the dots, you have the shape. They'll give you credit. It's not an art class. It's not AP art. Sure. Okay, so that's sine. Easy peasy. Let's hope cosine looks nicer. Cosine of 0, 1. Cosine pi over 2, 0. Cosine pi, negative 1. If you can't say it this quickly and this confidently, that's a bad sign. Cosine 3 pi over 2, 0. Cosine 2 pi, back to 1. And it works its way backwards like this. It's really hard to draw with this new pen. All right. I think it looks better on large. For the most part, it was better. I don't know. Maybe I'm just deluding myself. Sure. Something like that. It's better than that guy. All right. So that's cosine. Cosecant. Now, a lot of teachers will teach you some ways I don't like, some ways I do like. I don't know. Anytime we hit 0, cosecant is going to have an asymptote. Why? Because it's 1 over sine. So these graphs are super related. So I'm going to have an asymptote here, because that's 1 over 0. I'm going to have an asymptote at pi, because sine of pi is 0. I'm going to have an asymptote at 2 pi. And see, the asymptote's repeating every pi, because the 0 is repeated every pi. But the shape of the graph, just like this one, repeats every 2 pi. But the asymptote repeats 2. That's something I'll be looking for if you do this. Now, what's another key point here? Well, sine of pi over 2 is 1, so cosecant of pi over 2 is also 1. And we're kind of flipping all these values over. So some teachers will teach you to just build it on top of your sine, and that's fine. That's exactly what it should look like. So sine has a relative max, cosecant has a relative min. I can't draw this to save my life today. It's hard because I'm not writing on the screen. Too much information. Like that. -1. That's pretty good. I'm pretty happy with that. Back to -1 again. See, these are 2 pi away. So we're bending like this, just some nice parabola-like shapes. And we're bending like this. So again, in case you weren't following earlier, sine of -3 pi over 2, 1. 1 over 1 is 1. The values are getting bigger. Why can't I do it? Whammo. Cosecant. Secant is the same story over here. I don't know what color. Purple. So we're talking about this shape. Wow. This is the best thing I've drawn so far. We're talking about that shape on top of each hill, on top of each relative minimum, maximum. And the same story. Whenever cosine hits 0, secant will hit infinity, will hit undefined. Sure. Bend the asymptotes. I'm just making my asymptotes first. Every time we had 0 on cosine, which wasn't there. Uh-oh. Okay. Right. I knew I should have recorded today. This is the day before the Unit 8 tests, in case you're keeping score at home. All right. So this guy flips up. We're talking about this shape. It's very similar to cosecant. It's shifted over, just like cosine is very similar to sine, just shifted over. Now we have this one. At 2 pi, we will be back at 1. It would keep going like that, with parabola type shapes all over the place. And then like this. Ta-da! We got through it somehow. Hooray. I wonder how much I'm going to edit this, if I will. At all. Probably not. All right. Tan. Much uglier graph. Same idea, though. What's tan of 0? 0. What's tan of... Uh-oh, look at the scale. This is pi over 4. 1. What's tan of pi over 2? Quick. Did you get it? It's undefined. So here's another asymptote for us. Tan of 3 pi over 2, -1. Tan of pi, back to 0. I don't like where that dot is. Tan of negative pi over 4, -1, pi over 2. So all the action happens within an interval of pi. These are asymptotes. And then tan kind of looks like that. Probably prettier than that. Smoother here. It's always been the story with art. I can see it in my brain. I just can't make my hand do it with these new instruments. And then repeating over here. These two. Like that. Oh no, that looks better. It's usually better if I'm not trying to hit dots, to be honest. So what does cotan do? Well, same rules as before. We're going to look whenever tan hits 0, we're going to have an asymptote. We're going to have an issue. So pi at negative pi. And cotan of 1 over 1, still 1. This is hard for people. Cotan of pi over 2 is 0. I notice people messing that up. And then cotan of 3 pi over 2 is negative 1. So cotan kind of does this thing where it flips around what tangent was doing. That one looks like a million times better than any of those. Why? Disappointment. All right, and then something like this. Nope. Okay, I was just about to check myself. I was like, is it going because I'm going left and right? It's better. Again, try not to hit the dots. All right, so each of these guys has a period of pi, and we're going to try to move on. Hooray. Your calculator can produce these much nicer, obviously. But again, you need to be able to produce these by hand. That's the main takeaway I have for you. Here we go. So here's a chart talking about how to transform these. This is the same basic idea you've been using all year, except with this period column. The period will be 2 pi divided by this coefficient. Notice for each of these guys that I have b factored out. In some of your pre-calc courses, it goes more like this: a sine bx plus c plus d. And in that case, it changes some of the formula. It doesn't change a whole lot. It makes the horizontal shift a weirder formula, but everything else is pretty much the same way. So we're going to make sure we factor out b so we can follow the book's format. If you're doing it this way, you're probably not going to get that much wrong. So when c is positive, the horizontal shifts to the left. Same thing we've always done. If we're adding on the inside, it shifts left. When c is negative, the horizontal shifts on the right. The horizontal shift's often called the phase shift for periodic functions. Just some terminology you'll hear mentioned. Notice these two guys have the same thing. These all have the same thing. What's key difference? These two guys don't have amplitude. Amplitude is the distance. It's the distance from x-axis to peak. Okay? And these guys don't have that because they go on forever. Period difference. This guy is the only one with a different period. Whoops. That was in the highlighter. That guy's the only one with a different period. These two guys have the same period. All the same, all the same. Okay, it's not really something to stress out about. It just should be review. You will have questions on this. So, how do we do sketching of the graph without a calculator? Without a calculator. So the first thing I would notice here is that I have my insides are dividing by 2. So b equals 1/2. So my period is 2 pi divided by 1/2. Or it's 4 pi now. So it's going to take 4 pi for things to repeat. You can try to plug some stuff in, especially when they give you away the axis like this. What's cosine of 0 when I plug in x equals 0? Cosine of 0 is 1. 1 times negative 5. So now we're down here. The next value kind of suggests me to take is pi. Cosine of pi over 2. Pi over 2 is 0. 2 pi, I'm getting cosine 2 pi over 2. Cosine pi is negative 1. We're getting 5. And cosine 3 pi over 2, 0. Cosine 4 pi over 2 is the same as cosine 2 pi. But I know from the period calculation I just did, it should repeat. So basically what happened, we flipped it over. We increased the length of time it takes to do its thing. Something like that. We increased the length of time it takes to turn around to repeat. And we made its amplitude a lot bigger. The amplitude for this function is 5. And I'm going to jinx it again. Yep, okay. Because you know what I was thinking? Wow, I'm graphing so much better. Heaven forbid I think that. All right, so it's a wavy little function like that. Easy peasy. A little more complicated. Not so bad, though. Not so bad. What am I going to do? Again, if you have a pre-calc technique you like, go ahead and do that. Here's how I'm going to teach you. Factor out a 2 on the inside. 2t divided by 2 is t. Pi over 2 divided by 2 is pi over 4. Okay? So c equals pi over 4. That's the phase shift. We're shifting to the right by pi over 4. I'm subtracting pi over 4 on the inside. And what's this 2 doing? My period equals 2 pi over 2 or pi. It takes me pi to repeat now. So again, plugging things in, not the worst to get started. If t equals 0, we have sine of 0 minus pi over 2. Sine of negative pi over 2 is just negative 1. So that's indicative that we moved things over. And then all the important pieces are moving over by pi over 4. What does that mean? What's sine of pi over 4 now? What's when we plug in t equals pi over 4? T pi over 4 would be 2 times pi over 4. Pi over 2 times pi over 4. That's what I'm saying. 2 times pi over 4 minus pi over 2. We have sine of pi over 2 minus pi over 2. Sine of 0. So pi over 4 is 0. So it's going to shrink down our function by a factor of pi. It repeats in pi. It has to repeat in shorter amount of time. Yep, that's what I get for thinking I was doing better. Womp, womp, like that. Oh, so good. If you say womp, it does help. It's a statistically proven fact. 50% of the time, it works every time. And so I'm just repeating the points I see over here. If they are pi away from each other, pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, repeat. And it just cycles through. It's not that bad. If you can get the period, if you can get the phase shift, it's not that bad. Whoa, don't go up. Don't go up from there. Womp. See, that was so good until I stopped saying womp. All right, this video is so long. All right, look at that though. The pressure. All right, let's wrap this up. One more slide. We'll do lots more examples of graphing in the homework. Don't give in, don't use a calculator. Focus on the period, focus on the phase shift. I know this video is goofy. I'm sorry. So sine and cosine are related with the basic Pythagorean identity. Whether it's expressed with thetas or whether it's expressed with x's, this is super important. You can use this to get all the other important identities. If we divide by cosine squared, sine squared over cosine squared, tan squared. Cosine squared over cosine squared, 1. 1 over cosine squared, secant squared. This is the other only identity you have to know. If you felt like this class was going to be a lot of identities, it's not. It's only these ones. It's only these ones. So they ask you in this problem to use the Pythagorean identity to rewrite this in a form with only one trig function. One trig function. Then without using calculator, solve for theta. All right. So your goal is to make this say only cosine or only sine. 3, 2, 1. It's okay if you got stuck. This is weird. I'm not sure many pre-calc courses go this deep. Cosine's kind of stuck here. So what we're going to do is we're going to rewrite sine. Can you rewrite sine? Well, I know sine squared equals 1 minus cosine squared. That's why these are the only ones you have to know, because you can solve them. You can make any other identity out of this line, this one. So sine squared equals 1 minus cosine squared. That's the substitution we're going to use. If that's where you had stuck, try it again. Try it out now. It's just algebra from here. Okay, I'm gonna go. So pause the video now. Last chance. So I distribute the negative. And now this should look familiar to you. This should look like, and again, this is very silly if you have to actually write this out when you get started. It looks like 2x minus 1 plus x squared equals negative 2. It's a quadratic if x was cosine theta. So we're going to make this look like that. We're going to rearrange everything. What would you do here? You would solve for 0. We're going to get 0 on one side. And I'm going to rewrite this in highest to lowest terms. 2 cosine theta plus 1. And then you could try to factor this. This is x squared. So if you can't see it, this is x squared plus 2x plus 1. Can you factor that? If you really haven't done anything yet, pause the video, try it out. 3, 2, 1. You should have gotten cosine theta plus 1 squared equals 0. That's how this factors. This is x plus 1 quantity squared. So cosine theta equals 1. Sorry, cosine theta plus 1 equals 0. Cosine theta equals negative 1. Who's that theta? Theta should equal pi. Okay? And that's it. Use a calculator to verify your solution. How are we going to do that? We can graph both sides. So we're talking about graphing 2 cosine theta sine squared theta in y1. Please keep watching. I know the video's gotten long. 2 cosine x. The calculator doesn't really care if it's theta. Don't worry about how to get theta. How do you type this in your calculator? You need to type it like this. Parentheses, sine x. Then square it. It needs to look like that. And on the other side, we're going to graph negative 2. Here's a hint. Zoom, this is why I asked you to keep watching. Zoom 7 is called Z trig, zoom trig. This will give you a nicer output. And where do we have our answer? Well, we have multiple ones, But what's the right window? We should be going from 0 to 2 pi. Graph again. Only that one solution. Second trace. Intersect. It's already there. That's the advantage of doing zoom trig. It's already right in the center of the window. 3.141. 3.142. Tomorrow is Pi Day. Happy Pi Day. Thanks for watching the video. You're a champion if you stuck through it. I'm so sorry for my graphing abilities. I'll get better with this thing, I promise. Have fun with the homework. Have fun with the review. I'll talk to you later. You have a great night. Have a great time with the homework. Bye for now.